The next topic is section 5, Cauchy-Euler equations. What is Cauchy-Euler equation? It's a differential equation that looks like this. At squared y double prime plus bt y prime plus cy is equal to 0. The second derivative y double prime comes with the second power t squared. The first derivative y prime comes with the first derivative t, and the zeroth derivative, or the original function, y, come with t to the 0 power. Nothing is here, which means t to the 0 power, or 1 is hidden. Divide each term by at squared, then we get this form. The equivalent. This thing is called Cauchy-Euler equation. Okay, how do we solve it? We're going to talk about two different methods. Change of variable method, which is the default method of our textbook author. And the second is linear independent method. I don't think it is in our textbook. Maybe it is, but I can't find it easily. It may be buried somewhere. But we're going to talk about it in two different methods. Textbook method is here. Change of variable method. And let's go. We take the change of variable. T is equal to e to the x power is a change of variable, or equivalently x is equal to log of t. Now if you do that, and you can express your function y of t differently, we take z of x as y of e to the x power, but what is e to the x power? That's equal to t. So we end up with this expression here. Z of x is equal to y of t. The same function, same quantity, except that the independent variable is written a little bit differently. Okay, how does it help? If you take the derivatives, you're going to get something like this. Take the derivative z prime of x, and that's the same as taking the derivative of y of e to the x, this one. And by the chain rule, this is what we are going to get. Derivative of the outer function, y prime, inside always stay the same. And by the chain rule, we multiply the derivative of the inside. So what do we get? E to the x power times y prime of e to the x. And e to the x is equal to t, and e to the x is equal to t, yeah. So in the end, what do you get? Z prime is equal to t, y prime of t. And here is the first substitution to make. Let's see. Back in this Euler's equation, t y prime is right here, isn't it? And that's going to be replaced by z prime. And let's see. Okay. And then that part is going to become z prime. That's what this computation accomplished. Just a chain rule. Now let's take another derivative. Z prime is equal to t y prime of t, or equivalently speaking, e to the x times y prime e to the x. Let's take the derivative here using the product rule. Second derivative is the derivative of the first function. This exponential stay the same, and the second function stay the same. So exactly the same thing was repeated. This is a derivative, which happens to be the same as before, and this one always the same as before, plus first function stay the same, and the derivative of the second function. How does that work? using the chain rule, derivative of y prime became y double prime, and then inside stays the same, so e to the x stayed the same. And by chain rule, we multiply the derivative of the inside, that's e to the x. So if you simplify, what do you get? E to the x, y prime e to the x, that's the same as z prime. And how about this? E to the x, another e to the x, that's t squared times y double prime. That's what we got. Let's solve for this quantity, t prime y prime. Then all you have to do is flip the z prime to the other side, and what do you get? T squared y double prime is z double prime minus z prime. This is what we get in the end. T squared y double prime is equal to z double prime minus z prime. So here, this quantity here is the same as z double prime minus z prime. I thought this one was blue. Is it already blue? I can hardly see the color. Okay, so ty prime is z prime, t squared y double prime is z double prime minus z prime, and cy, let's see, z of x is actually the same as y of t, is it? So this y, which now I'm highlighting in green, is the same as z. Do you see all those colors here? This is red, that's blue, and that's green. I can't see very well. Okay, now it's better. Now, if you look at the second equation here, no more variable. We ended up with a linear equation with constant coefficient. And then, if we rearrange, we get this equation. A z double prime plus b minus a z prime plus cz is equal to 0. So this is a linear ODE, second order linear ODE with constant coefficient. So you can use it through the method of characteristic. Now, how about the second method here? Linear independence method. Just like we did earlier, with a bit of an educated guess, we plugged in y is equal to e to the lambda t power. We make another educated guess here. In this equation, where's the equation? Excuse me. Yeah, here we go. Euler equation here. Plug in y equals to t to the mth power. Here, oh, it's already here. Okay, well, I don't need it. In this equation, plug in y equals to t to the mth power. Y prime is therefore this derivative computation. That's easy. And y double prime is this derivative computation. Again, it's pretty easy because they are just power rules. Consequently, the original equation becomes this way. Y double prime, which I am highlighting in red, is going to be replaced like this. M m minus 1 times t to the m minus second power. And then this y prime, this blue term, is going to become m t to the m minus first power. And then this one, oh come on, which I'm highlighting in green, is t to the mth power. Okay, so this is the original function. Y is t to the mth power. Take the derivative. Take the second derivative. And plug those in, and this is the equation. Now put this t to the second power times m minus second power. What do we get? What do we get? Multiply this, and I'm gonna get just mth power. How about this t? Multiplied, I'm gonna get just t to the mth power. We're almost there. We factor out the common factor t to the mth power, and what's left is this equation: am m minus 1 plus bm plus c. Or if we expand, then we are gonna get the same characteristic equation as before. As a matter of fact, am to the second power plus b minus z times m power plus c is equal to 0. This one, same characteristic equation as before. Either way, we are going to get the same characteristic equation. This one, the same thing as before. Or t is constantly 0, we get a trivial solution. Many people miss this trivial solution, by the way, and I remember I missed it when I was taking this exam here, and I missed that, so I lost some point when I was a student, so I remember it. Anyway, okay. Now that we have this characteristic equation, what we can do is to solve it and then find out the eigenvalues m, and then you're gonna get a proper solution. Now, if you use the linear independence method, we get this linear combination directly, because we use t to the m power to begin with. So c1 t to the m1 power plus c2 t to the m2 power. And then what if we have double root tmth power tm, and then here somehow we get log of t, and that part is a little bit unclear. But if we use the change of variable method, that becomes rather clear. If we have m1 and m2, we have z is c1 exponential, c2 exponential like this, and then e to the m1 power x is the same as e to the x times to the mth power, e to the x to the mth power, generating t to the mth power like these. But then again, if we have this double root, it really shines here. Exponential and x times exponential. Exponential, as we saw before, is t to the mth power. But what about this x? That's logarithm. Remember this? T is e to the x power, but x is log of t. So this is log of t. And what do we have? We have this expression for double root. How about complex root? If you use the linear independence method, this may be a little bit hard to get. This too wasn't that easy. But if you use the change of variable method, this becomes really easy. Okay, I take it back. It's not really easy, but is natural. We have exponential and another exponential, but they turn out to be complex case. In that case, we have sinusoid, sine and cosine. So e to the lambda x times cosine of omega x, e to the lambda x, same real part, times cosine of omega x. And then put those together, what do we get? The exponential is t to the lambda power, the same thing we saw before. And cosine of omega x, but x is logarithm, isn't it? Log of t. So cosine of omega, log of t, sine of omega, log t. There goes the solution in general form. Okay, how about some example? Do we have time for example? I don't know, let's try. Solve the equation, and here is Euler's equation, and this time, oh boy, I ended up giving a cubic case or third order Euler equation. That's okay, we can do it. Third power, second power, first power, zero power here. So it's an Euler equation. Okay, how do we handle this? Linear independence method. Okay, all right. Plug in y equals to t to the mth power. And the third derivative is not too difficult. There you go. Take the derivative 3 times using the power rule. M, m minus 1, m minus 2. And then the second derivative. Here it is. M, m minus 1. And then first derivative. Just multiply m. Okay, we have that. And then what do we do next? This t to the third power minus 3 cancel out, we get this. This t squared and then minus second power cancel out, we get that. This t power and then this minus 1 power cancel each other out, we get this. And what do we have? We have t to the nth power in common, take it out. And what's left is a polynomial of m. Okay, let's break it off and then factor it again. Break it all off, we get that. Okay, I'll leave the computation to you. And then some further simplification, we get this. M cubed minus m squared minus m plus 1. Can we factor it? Not too bad. We can group like this. First 2 and the next 2. First 2, m squared m minus 1. Next 2, just negative m minus 1. Put those together. M minus 1, m squared minus 1. And then factor further. Perfect. M plus 1 times m minus 1 total quantity squared. So what do you get as the eigenvalues? M minus m equals minus 1, or m equals 1 as double root. So minus 1, what do you get? T to the negative first power, okay. How about the double root? T to the first power, or t to the first power times log of t. We have this log of t. And general solution. We can express it as a linear combination. Or we can have this y constantly equal to 0, a trivial solution. The following mathematical program verifies it. Well, turns out to be 0. Yes, left hand side of the ODE, calculate it out, and right hand side is of course 0. Well done. How about the other method, change of variable method? I guess I'll have to leave that to you. Long and complicated, so I don't really want to deal with it in detail, as a matter of fact, to tell the truth. For third order, this change of variable method is, I don't know, it's as you can see, it's kind of like this. So I'll leave this to you, and I'll encourage more students to use this linear independence method. And this method corresponds perfectly to what we already did earlier in section 3, general solution theorem.